G'day chemists, welcome to IB question of the day. Here we have a series of, well, a question, but from a paper 2, but it's like a series of sub-questions, and it's equilibrium, and equilibrium always makes me really happy. I like equilibrium. Okay, so here's our question. This is your chance. Sort of pause the video, answer the question, and then we'll come back and we'll check our work. So we're obviously going for a small section, like 5 marks out of, I think this question's like 17 marks. Ammonia is manufactured by the Haber process. Here's the reaction that we know super duper well. Nitrogen gas plus 3 hydrogens as gas goes to, but equilibrium style, to 2 ammonia molecules as a gas. The enthalpy is negative 92 kilojoules per mole. I think you'd be hard pressed to find a chemistry teacher who's been doing the job for a while who doesn't know that enthalpy off the top of the head. It sort of pops up all the time. And outline what is meant by dynamic equilibrium. So a definition question, right? Then deduce the Kc expression, so the equilibrium constant, for the reaction in part D, or D1, so just above. And the Haber process requires a catalyst. State how catalyst functions. And finally, we're going to finish. So those are all 1-mark questions. Then we're going to finish it off with a 2-mark sketch a Maxwell-Boltzmann distribution curve showing the activation energies with and without a catalyst. So there's 3 things to do on that, really, for 2 marks. Yeah, okay, so let's have a look. So these 3, I'm not going to show what are they called? The marking criteria. I'm going to highlight the parts where the marks come from. So, outline what is meant by dynamic equilibrium. A reversible reaction in a closed system where the rate of forward reaction equals the rate of reverse reaction. So, closed system, rate of forward reaction is equal to the rate of reverse reaction. Those were you obviously had to have it as a statement, but those were the things that it had to make reference to. The fact that it was a closed system and forward and backward reaction are moving at the exact same rate. So deduce the Kc expression. Nice and straightforward. You need the whole thing here. So we've got Kc equals square brackets, meaning the concentration of ammonia squared, because it's got this 2 here, right? So it's like concentration of the products over reactants. So products over reactants equals K. That's why I call these like pork is what I use to remember this. Product over reactants equals K. So concentration squared, because that's the coefficient at the front, over concentration of nitrogen gas times the concentration of hydrogen gas cubed, because we've got this 3 as a coefficient just here. So the Haber process requires a catalyst. State how a catalyst functions. Catalyst provides an alternative pathway that lowers the activation energy. Okay, so an alternative pathway lowering the activation energy. Do you know what? I would even add this. So a catalyst provides an alternative pathway lowering the activation energy that increases the rate of reaction. That's a better sentence right there. But the marking criteria was just looking that you showed alternate pathway lowering the activation energy. So you still had to say what it did, but those were the explanation points it was looking for. And there we have sketch a Maxwell-Boltzmann curve showing the activation energies with and without a catalyst. Okay, so M1 comes from the correct shape of the curve, right? In these ones, we need to make sure the curve is touching the origin on the low kinetic energy. At the high energy, it does not touch the x-axis. Okay, and that when we show where the activation energies are, catalyzed is less energy than uncatalyzed on the x-axis. So, I mean, draw it smoother than that. That was trying to draw on the computer. It's a bit trickier. And see how it touches down here, but not here. And then we go, here are our activation energies. Now, I mean, what it's showing is like this is with a catalyst, right? Right here. This is uncatalyzed. But you can see that like in the uncatalyzed, what's going on is this fraction of particles is above the activation energy. So they're the ones reacting. But when we add a catalyst, it's, you don't need to highlight this. This is just me showing you. This section is the amount of, well, this sort of area under the curve, that's the amount of particles which are reacting. So the takeaways there are to make sure that we're writing in full sentences, we're writing paragraphs, we're writing full explanations, we're not just giving what we think the key phrases are. All right, if you have any questions, put them in the comments below. All right, if you have any questions, put them in the comments below, or if you're one of my students, send me an email, and we'll get back to you as quickly as we can. Thank you for watching. Don't forget to subscribe so you keep getting the questions of the day, and yeah, we will see you tomorrow. Actually, we'll see you after the weekend. Bye now.